This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on points of inflection. Our first example is going to be the function f of x equals x cubed, and let's take a look at the graph of that function. You'll notice it is concave down when x is less than 0. It is concave up when x is greater than 0. The concavity changes at 0. That's what a point of inflection is. There's one other thing to consider, namely that the second derivative of this function is 0 at 0. So those are the conditions we're going to look for to determine whether or not something is a point of inflection. So again, to recap, f of x is concave down. It looks like a downward pointing parabola whenever x is less than 0. Concave up when x is greater than 0, and indeed the second derivative, if you do the first derivative, 3x squared. Second derivative, 6x. Plug in 0, you get 0. So the second derivative of this function at 0 is 0. Those are the conditions we're going to look for to determine a point of inflection, identifying when the second derivative is 0 and showing that the concavity changes. So in this case, we will conclude there is a point of inflection at x equals 0. So here's our process in general to identify a point of inflection. Find all points such that the second derivative of the function is 0. And then if the concavity changes at that value, then that value is a point of inflection. We'll look at the concavity a little bit to the left of the value. We'll look at the concavity a little bit to the right of the value. If the concavity changes, then we have a point of inflection. So here's our next example. F of x is x cubed plus 9x squared minus 4x plus 7. If we want a point of inflection, we need to get the second derivative. But of course, let's get the first derivative. 3x squared plus 18x minus 4. Second derivative will be 6x plus 18. Now I want to find the point of inflection, so I'm going to set the second derivative equal to 0. Solving for that, adding negative 18 to both sides, we get negative 18 is 6x, and divide by 6, we get negative 3. So this is a point where the second derivative is 0. That is not enough for it to be a point of inflection. We need to show that the concavity changes. That is a candidate to be a point of inflection. It is a possible point of inflection. So I choose numbers on either side. So my critical number, in a sense, is where the second derivative is 0. And if there were any places where the second derivative didn't exist, those would also be critical values. But in the case of polynomials, the second derivative will always exist. A little bit to the left of negative 3 is negative 4. A little bit to the right of negative 3 would be 0. And I want to find the second derivative at each of those points to determine what is the concavity on each side of negative 3. Second derivative at negative 4 is 6 times negative 4 plus 18. Negative 24 plus 18, or negative 6. So at negative 4, the function is concave down. Second derivative is negative. Function is concave down. We'll identify it with that symbol. Now the next test point is 0. Plugging in 0 into the second derivative, 6 times 0 plus 18 is 18. That is a positive number, so it will be concave up at 0. Does that satisfy our conditions? Is there a change in concavity? To the left, it's concave down. To the right, it's concave up. At the point itself, the second derivative was 0. So indeed, we conclude that there is a point of inflection at x equals negative 3. If we were graphing this, we'd actually plug the negative 3 into the original function to find out what the y value is. But indeed, we know there's going to be a point of inflection, a change in concavity, when the x value equals negative 3. Our next example is f of x is x to the fourth minus 10x cubed plus 24x squared minus 5x plus 9. We need to take the second derivative and set it equal to 0. So our first step is to find the first derivative, 4x cubed minus 30x squared plus 48x minus 5. Let me fix that. And that's fixed. But to find our point of inflection, we need to set the second derivative equal to 0. F double prime of x will be 12x squared minus 60x plus 48. Factoring a 12 out, that will give me x squared minus 5x plus 4. Setting it equal to 0 first, of course. Point of inflection is when the second derivative is 0. Then factor out the 12. Factoring this, we get x minus 4 times x minus 1. So if that equals 0, either x minus 4 is 0 or x minus 1 is 0. So my candidates for points of inflection are x equals 1, or x equals 4. But for it to be a point of inflection, I need to show that the concavity changes when I go across those values. So here's our original function, here's our second derivative. We had x is 1 and x is 4, so we will choose numbers in each interval. To the left of 1 I chose 0, between 1 and 4 I chose 2, beyond 4 I chose 5. We will see what the concavity is at each one of those points by plugging those values into the second derivative. So f double prime of 0, 12 times 0 squared minus 60 times 0 plus 48 is 48. So at 0, the function is concave up. We see that. Second derivative is positive, it's concave up. Next example will be the second derivative at 2. Second derivative at 2, 12 times 2 squared minus 60 times 2 plus 48. 2 squared is 4, 4 times 12 is 48, minus 120 plus 48 gives us negative 24. So if that's the case, the function is concave down at 2. So let's look at this value 1 for a second. The second derivative was 0, and the concavity changed. To the left it was concave up, to the right it was concave down. So at this point we know we have a point of inflection at x equals 1. But there's one more point for us to look at, to check. Beyond 4 we have 5. So the second derivative at 5, f double prime of 5, is 12 times 5 squared minus 60 times 5 plus 48. 5 squared is 25. 12 times 25 minus 300 plus 48. I believe that's 300 minus 300 plus 48, which will just give us 48. So if that's the case, we have a concave up situation at 5. And notice that the concavity changed again. To the left of 4, the function was concave down. To the right of 4, the function was concave up. So we also have a point of inflection at x equals 4. So again, to restate our conclusion, there is a point of inflection at x equals 1. If you'd want the y value when x equals 1, plug it into the original function. There is also a point of inflection at x equals 4. And again, if you want the y value, you would plug that into the original function. Let's take a look at one more example. This time we have f of x is x to the 4th minus 8x cubed plus 24x squared minus 7x plus 11. We want to find all points of inflection. So let's remind ourselves of the process. Find the second derivative, set it equal to 0 to identify the candidates, and then check to make sure that the concavity changes on either side of that potential point of inflection. First derivative, 4x cubed minus 8x squared plus 48x minus 7. Second derivative, 12x squared minus 48x plus 48. We need to set that second derivative equal to 0. And now we're doing some algebra. We will factor a 12 out of the right-hand side. So we get 12 times x squared minus 4x plus 4. Our next move is to factor that, and that's x minus 2 times x minus 2. Setting that equal to 0, we get x minus 2 is 0 or x minus 2 is 0. So the only candidate that I have for a point of inflection is x equals 2. The second derivative there is 0. But is that a point of inflection? If it is, I have to show that there's a concavity change when I go on either side of 2. So there's our original function, there's our second derivative. Our candidate is 2. We're choosing numbers on either side. To the left of 2, I'm choosing 0. To the right of 2, I'm choosing 3. If I plug in the 0, what is my second derivative? 12 times 0 squared minus 48 times 0 plus 48. My second derivative is 48, which gives me a concave up section. So to the left of 2, this function is concave up. Beyond 2, I'll choose 3. We'll take a look at the second derivative at 3. 12 times 3 squared minus 48 times 3 plus 48, which is 12. It's also concave up. So we have a situation here where it's concave up to the left and a situation where it's concave up to the right. The concavity does not change. It is always concave up. Since we have no concavity change, we conclude that there is no point of inflection at x equals 2. And taking a look at the graph, you can see that it is always concave up. We never have a situation where the concavity is going to change. Moving beyond that way, again, you can see the graph is always concave up. So indeed, this problem has no points of inflection because the concavity doesn't change. The second derivative at 2 was 0, so it kind of flattens out. It's almost like a straight line. So it has no concavity there, but is concave up to the left, it is concave up to the right. So there is no point of inflection. And that will conclude this lesson.